Oh, hello. I was just reading a little something about quantum computing. And now maybe I can tell you a little something about it if you're curious. So quantum computing, what is it? How does it work? Is it just another step in our current evolutionary development of parallel processing computers? Or is it something completely different that is going to change our paradigm of parallel processing forever? Now, there's a lot of hype around quantum computing. If you know anything about it, you've probably heard a lot of wild claims about what they can and can't do. Usually what they can do, because people say they're like magic computers that can do pretty much anything. People have said even that having a quantum processor is like having a traditional processor in which all the transistors are like multi-core processors in and of themselves. And they accomplish this by harnessing the power of the atom. Now, before we quite get into how they really work, maybe we should take a quick look at where we are in computing now. Now, back in the 1970s, co-founder of Intel, Gordon Moore, proposed a theory that the number of transistors on an affordable CPU would double every 2 years. And to a great extent, he has been accurate in that prediction. Now fast forward to today, and we can see the massive gains in processor clock speeds from the 740 kilohertz range back in the 1970s to the 2.5 gigahertz range of the early 2000s. But we started running into a problem with all these massive speed gains. Now, what we discovered basically is that there's only so much electricity you can cram through a processor before it basically starts to burn out. So, enter the parallel processing computer. Now, parallel processing really isn't anything new. Pretty much since there has been more than one computer hanging around, some guy pointed at him and said, "Hey, why don't we hook them all together?" Thus, parallel processing is born. Again, today, you will be hard-pressed to find any computer that does not have a parallel processing core in it, otherwise known as a multi-core processor. Now, as with everything, there are some drawbacks with multi-core processors. The most significant probably being with our current development of parallel processing is best described by Amdahl's law, which basically states that the amount of speed up for a program that is being run on a multi-core processor is always going to be limited by the amount of code that isn't specifically written to be parallel processed. Sounds pretty smart, doesn't it? But is this the only avenue of development for computers? Richard Feynman, the acclaimed theoretical physicist, stated that there are some things that just cannot be represented on a classical computing machine. And that is where quantum computers come in. So back in the 1980s, the idea for quantum computers were first put forth by theoretical physicists Yuri Manin and Richard Feynman. And essentially, a quantum computer is a computational device that operates using subatomic particles to perform massive amounts of simultaneous calculations, as opposed to the transistor-based traditional computers. But before we get into quite how they work, perhaps we should look into some of the difficulties faced in actually building a quantum computer. When building a quantum computer, we run into much the same problems that we do when building a classical computer. But as it is with computer engineering, the more complex a system gets, the more difficult its implementation. And it's hard to find a more complex subject than quantum mechanics. First of all, just like with a traditional computer, we're dealing with extremely tiny parts. With traditional computers, we have transistors. And with quantum computers, we're dealing with the smallest particles known to man. Now, most every electrical device has to deal with at least these two problems, and that is interference and cooling. And the more delicate the instrument, the more interference that we can expect. As with your traditional processor, something as small as a speck of dust or a hair or even the oils from your fingers could cause your processor to overheat and burn out. But when dealing with something as small as an electron, a speck of dust can be like a boulder the size of Miami. And that's pretty big interference. Also, you can expect interference from even such things as the room temperature thermal radiation, which means your requirements for cooling get pretty extreme. For example, the D-Wave 2 quantum computer needs to be housed in a refrigerator cooled to 150 times colder than interstellar space, which is 0.02 Kelvin, which is pretty darn cold. So quantum computers are really hard to build, but how do they work? Now, as we said before, a classical computer operates using transistors. A transistor that is like a switch that can be either on or off, which is how we get our binary representation of 1 or 0, on or off. Now, with a quantum computer, they use what's called quantum bits or qubits, which can be aligned in a magnetic field to manipulate what is called the spin on that particle into its lowest energy position, which they call spin down. And by applying a little bit of energy, they can shift it into its highest energy position, which they call spin up. That way, we can get the same interpretations as we do with traditional computers of a 1 or a 0. Here's where it gets interesting. Due to a phenomenon known as quantum superposition, these qubits can actually exist in more than one state at the same time, meaning that conceivably it can be both a 1 and 0 simultaneously. Now, this is what gives the quantum computer its amazing ability for massive calculations. And the information scales exponentially with the number of qubits that you have. So if you have n qubits, you can represent as much information as 2 to the n classical bits. So if you have only as much as 500 qubits, you can process as much classical bit information as there are particles in the known universe. Now, it's this idea that has given rise to the claim that a quantum transistor is like a multi-core processor in and of itself, because it can represent more than one value at the same time. But before we get carried away with the idea of having 2 to the 500 processors in our computer, it's time for a bit of a reality check. Before qubit system is measured, they exist in a state of quantum superposition, represented by a coefficient of relative probability of finding that qubit in one state or another. But once they are measured, the qubits will fall into either the spin up or spin down state. Now, this concept is best represented by use of the Schrödinger equation. But for the rest of us without theoretical physics degrees, Schrödinger gave us a much simpler way to understand this concept by way of a thought experiment that has since become very famous. Now, this thought experiment has been since known as Schrödinger's cat, where he proposed that you put a cat in a box, and inside that box is a vial of poison attached to a trigger. Now, that trigger may or may not go off, smashing that vial of poison and killing the cat. But you won't know whether that cat is alive or dead until you open the box. So, until you open the box, you can think of that cat as being both alive and dead at the same time. Now, as you can see, our qubits are just like Schrödinger's cat, in that before we open the box and see what's going on, the cat can be both alive and dead at the same time. But as soon as we want to check on it and get the data that we're looking for, the cat must be one or the other, either a 1 or a 0. So as you can see, we run into the same type of limitations that we have in retrieving data from a traditional computing system. And what this means is that when writing a quantum algorithm, you have to write it in such a way that the result isn't one of these superpositions. It has to be something that can have an output of either spin up or spin down, an output that you can read, because you cannot read a quantum superposition. Now it's due to this concept that a quantum computer is not really a good replacement for a classical computer. In fact, some studies have shown that a quantum computer will actually perform slower in a lot of the day-to-day typical activities that we use a traditional computer for. And so that doesn't mean quantum computers are completely useless. Like Richard Feynman stated, there are some things you can't represent on a traditional computer, such as states of quantum physics. Also other types of calculations like massive amounts of comparisons that you need to do at the same time, or large-scale number factoring. But you also run into the same problem that we do with parallel processing, namely Amdahl's law, meaning that if you want to program efficiently for a quantum computer, you need to be writing quantum algorithms. And if you thought parallel programming was difficult, try programming for 4 dimensions. So in conclusion, while some of these things seem very exciting, and it might seem disappointing to burst this hype bubble of the magic computer that can do all these amazing things and give us super ultra mega HD and video games that we can climb inside of, it just is one of those cases of something that's just too good to be true. But it's good to know that we are actually still in a very good place with our traditional parallel processing computers, and there are a lot of advancements and avenues of development still to be explored in traditional computing. So thank you, and good night.